Hello everyone, for this tutorial video, I'd like to explain the chain rule for derivatives, whose proof is actually more tricky than meets the eye, because it involves more than two functions, even though most compositions involve only two functions at first glance. We start by defining the derivative of u of x using the literal definition of the derivative, seeing that if we subtract this derivative from itself, we get 0. Define a separate function v of h as exactly equal to 0 if h equals 0, and equal to this derivative if h does not equal 0. We see everywhere that h does not equal 0. We can rewrite u of x plus h as u of x plus h separately, and h is multiplied by v of h plus the derivative of u of x. We next do this again, defining a third function w of k as limit as k approaches 0 of function of z plus k minus function of z all over k minus itself if k is not 0, and literally 0 if k is 0. We see also, like above, that function of z plus k equals function of z individually plus k times w of k plus derivative of function of z. We now can define, using the literal definition of the derivative of a composition, which would be function of u of x plus h minus function of u of x, all over h as h approaches 0. We can rewrite the numerator using what we found earlier as function of u of x plus h times v of h plus derivative of function u of x minus function of u of x. We can substitute back in w of k plus the derivative of function of u of x in the second term in our addition. That is being multiplied by h. We see function of u of x cancels itself out. We substitute in this expanded form in the numerator of the derivative. We see this expansion allows us to cancel out the h's. We see as k approaches 0 and h approaches 0, the first term in the product equals 0. We see the limit of w of k as h approaches 0 is equal to w times the limit before it, which is w times 0, which is 0 as well. In conclusion, substituting everything back in, we have the derivative of u of x times the derivative of function of u of x. And so, this is our final result for the chain rule. The chain rule is more difficult to use not only because of how intricate its proof is, but also because you have to be very careful about what you choose as your inside and outside function. For example, if you want to differentiate the square root of 5z minus 8, you would see the inside function has to be 5z minus 8, and the outside function must be square root of x. It cannot be the other way. So we multiply the derivative of 5z minus 8, which is 5z, and the derivative of square root of z, which is 1 over 2 times the square root of z. But we see the catch is in this chain rule. We do not have simply 1/2 z, but rather we have 1/2 of 5z minus 8, owing to the fact the derivative of the outer function is actually the derivative of the outer function with the inner function as the input, and not the derivative of the outer function as normal. Now we have figured out how the chain rule works and computations you can use with it, we can move on to implicit differentiation next, which is actually an important application of the chain rule. Don't forget to subscribe if you found this video informative, and make sure to see other tutorial videos, and follow me on either Facebook or Twitter for more content.